My dear friends, welcome to Rajashekar classes on Applied Data Science with Python. This is lecture number 244. In this lecture, I will continue my discussion on how to use SNE effectively. If you recall my previous class, what we were saying that run SNE with various values of perplexity. And we also said that your perplexity must be less than number of data points. Number of data points. Let me continue my discussion. Just observe this one, what it says. The images above shows 5 different runs. This is original data. This is first run. This is second run, third run, fourth run, fifth run. Means we have 5 different runs output. But if you observe, in all the cases, perplexity is 30. We will try to understand this in detailed manner. Next important thing is, what if I keep my perplexity constant? If I keep my perplexity constant, just see here perplexity 30, perplexity 30, perplexity 30, perplexity 30. What does it mean? I am keeping perplexity constant. So if you look here, so again same original data set we are considering. I kept my perplexity as 30 every time, but I am changing my step. Just see, I am keeping step as 10, step as 20, step as 60, step as 120. Even we are keeping step as 1000. Step means what? We are changing number of iterations. So my number of iterations or step I am increasing with from 10 to 20. 10 iterations, 20 iterations, 60 iterations, 120 iterations, 1000 iterations. You will notice that this seems absurd. Which one seems to be absurd? Just see this one. Step 60. This seems to be absurd. What is the reason? That I have all the points grouped in small area. Just see, all the points are grouped. This is original data set. All the points are grouped in a small area here, small area here, isn't it? So the lesson is, always run your iterations till the time the shape does not change much. Just see, the shape does not change much here. If you refer at step 1000, the shape does not change much. Even for 1001 iterations, it will not change. Isn't it? Till the time the shape does not change much. So when I start here, step 10, just let me say like this. Yes. When I start here, just see, this is step 10. Isn't it? By 10 iteration, I got some structure like this. But don't stop here. Let it run till the time. So probability, I can say till the time, so probably 1000 iterations, you get a shape like this. Just see, you get a shape like this. And in 1001 iterations, these points do not move much. You must always try to identify stable configuration. So when you are analyzing SNE, plot your SNE for various values of step. That's what I am doing. Various values of step or iterations. I am taking different values of step. I am taking different number of iterations and see if the shape has stabilized. So that's very important. So first lesson learned was, always run SNE for multiple values of perplexity. Find the right type of perplexity by keeping your number of iterations large. and then change the iterations now to understand whether the shape is stabilizing or not. This is very important lesson. We discussed neighborhood embedding and key distribution to solve crowding problem. I already discussed this crowding problem in lecture number 241. What is this stochastic? Stochastic basically means, I can say, stochastic means, I can say, it is stochastic. Stochastic means it is probabilistic. I can say it is probabilistic. That is stochastic, isn't it? Probabilistic. This is one way of thinking about it. I can say in the place of stochastic, I can say it is probabilistic. So if you run SNE multiple times on same data set with same perplexity value, with the same step or same number of iterations, you could get slightly different results. This is important. With the same perplexity, same perplexity, same perplexity, same step. If I run my SNE multiple times, you will get slightly different outputs. Slightly different outputs. That's important. You could get slightly different results. That's because SNE is not a deterministic algorithm. You must understand this. SNE is not deterministic algorithm. As it is not deterministic algorithm, it produces different results for different runs. What's a deterministic algorithm? When the output, if I have an algorithm, if I give some data, let me say if I have an algorithm like this, let me rewrite again. If I have an algorithm like this, for this I am giving data. If it produce for all, I can say if I have an algorithm, let me say this is my algorithm. If I give it some data, if some data as an input, every time I run this algorithm, if I get the same value, same output, that's called deterministic algorithm. Every time if I get slightly different outputs, then I can call it as probabilistic algorithm or stochastic algorithm. So SNE is actually probabilistic algorithm. So that's why SNE does not do just neighborhood embedding, it does probabilistic or stochastic neighborhood embedding. So that's other lesson we should learn. Right perplexity and right number of steps. First you must identify right step and right perplexity. So here you learn that perplexity, say 30. Let me say perplexity is 30. Let me assume like this. Yes, perplexity here, if I say perplexity 30 is good, and number of iterations 1000. No, not this one. Let me assume this one is perfect. Perplexity is 30 and the step is 1000. Let me say like this. Perplexity is 30, good number of iterations 1000. For even if I increase steps, number of iterations, if there is no change, in the shape, if it is stabilized, I can say these two values fixed, isn't it? Now what you have to do, next lesson is after fixing perplexity and step. Now what you have to do, you run it multiple times. If you run this multiple times, you may get slightly different results. For same perplexity, for same step, you may, if you keep on executing this, you will get slightly different results. If you are getting slightly different result for same perplexity, for same step, means what does it mean? Basically, it is stochastic algorithm, because every time you run, there is a small difference in what the output is. So the next important lesson we have to learn from SNE is stochastic algorithm for same values of perplexity and step, you will get slightly different results, as it is probabilistic algorithm. I can say it is stochastic algorithm. I can say it is not deterministic algorithm. Now comes a scenario. We will try to understand another scenario like this. What it says, cluster sizes in t-SNE plot mean nothing. Cluster size, you need not worry, you need not bother about cluster sizes. Just see, so far so, but what if the two clusters have different standard deviation and so different sizes? Just see, here I have a cluster, here also I have a cluster. They have different standard deviations, they have different sizes. We will try to understand this simple example. Just see this one. Let me say like this. Yes, now comes a scenario like this. Now imagine that I have 50 points, just these 50 points, here 50 blue points, again I have 50 more other color points. I have 50 orange points. Let me say these are 50 blue points, this 50 orange points. I have two sets of points here. These orange points, observe carefully, these orange points are very, very dense, because I have packed all my points in a very, very small area. This cluster size is small, or this group size is small, because variance is small here. This you must understand. You must have small variance. You have small variance. That's the point here. Small variance, isn't it? This is the sparse. This one, just see this cluster. This cluster is sparse, isn't it? These are sparse points. So now what happens as I change my perplexity and I'm keeping my step very large. Let me assume my step is 5000 here. Just see, let me assume my step is 5000, large value. I'm keeping step as 5000, but I'm changing perplexity. Initially I'm keeping perplexity to perplexity 5, 30, 50, 100. We are changing perplexity, isn't it? Let me fix my which one? I'm fixing step. By the time I reached 5000 steps, the shape does not change much. Now I'm increasing my perplexity here. I'm doing everything from 2, 5, 30, 50, even 100. Now one thing you realize quickly, as I'm going, my 30 and 50 looks good. Just see, this is my 30, this is my 50. They look good, but there is one big catch here. If you see the shapes of my clusters, the orange points and my blue points, both of them typically have same density. Just see, my orange points for perplexity 50, my orange points and my blue points typically have same density. These two clusters have same density, but my original data set, observe here, my original data set, my orange points are much more dense. These points are much more dense, and my blue points are much more sparse. So one of the things that t-SNE does internally, it is basically expand dense clusters. Which one is dense cluster? This cluster is orange points cluster is dense cluster, and it will shrink the sparse clusters. I can say, let me write it like this: expands dense clusters. Expands dense clusters. This is my dense cluster, isn't it? And another one is shrinks or contracts. Shrinks sparse clusters. Just see, This is sparse cluster, it is shrinking. So what t-SNE is trying to do is it tries to, because it's also a stochastic neighborhood embedding algorithm. One of the things that SNE does is shrinks these sparse points. These are sparse points. It will shrink the sparse points and expand these dense points, isn't it? Because they are very, very dense, such that the densities of both of my group of points are roughly similar. Just if you observe for Perplexity 50, the density of both of the points are roughly similar. So one of the things that you cannot read from SNE is whether cluster is one of the thing. This is important. I will repeat. One of the things that you cannot read from SNE. You cannot read from SNE is whether a cluster is dense or sparse. You cannot get cluster sizes. You cannot get cluster sizes, isn't it? You cannot get cluster size. This is called this one. Just see here. This is called small cluster, and it is very, very tightly grouped. This is called large cluster, isn't it? So SNE imagine this was the data. This is my data set, original data set, isn't it? Imagine if you have never shown this. Let me assume this one. Imagine this was never shown. This is not shown. Original data set is never shown. Imagine if you have never shown this original data set. Imagine if you are shown this. Imagine if you shown at Perplexity 50. Imagine if this one only shown. One conclusion that I could have come to is, okay, my blue points are here. My orange points here at Perplexity 50, they well separated. This is the number. This is number one. Number two, they also roughly they have same density. Roughly, this and this blue points, orange points have same density. No, I cannot come to the same density conclusion. I cannot come to the same density conclusion. Don't misread SNE, isn't it? Because SNE tends to expand dense clusters and shrinks sparse clusters. So I cannot say anything about cluster size. This is very, very important. This is one of the drawbacks of SNE, by the way. We will continue our discussion in my next lecture on SNE only. Thank you very much.